on this page 5 about the difference between the round brackets with something and the square brackets with something and how it relates. So what I want to do first is I want to give an example of how to prove something's not a UFD, because this is kind of like a common qual question. And then I want to start in on modules over PIDs. But maybe since we're on this topic of this field, maybe I can show you something too. So yeah. So let me go back on this topic, and I just want to talk about companion matrices, I guess, for a second. So let's look at an example. So let F be a field. So I'm going to talk about companion matrices because it's kind of related to your question that you asked. Okay, so let F be a field, right? And let f of x be in f of x be a minimal or be an irreducible polynomial. Actually, I don't think we need it to be any polynomial. Be any polynomial. Okay, so it doesn't necessarily need to be irreducible. Okay, and consider. So here I'm gonna talk about companion matrices. This is what I'm getting into. And I'm going to talk about norms just for a second. Okay. So let f be a field, and let's be any polynomial. Okay. And let's say that f of x. Let's give it some letters. A0 plus A1. Oh, let's do B's. Let's do B's. So I'm going to use A's letter for something else. B0 plus B1x plus B2x squared plus ... plus bd minus 1 x to the d, and let's do bdx, or so let's suppose that it's monic, right? dbd minus 1 x to the d minus 1. So this is what's called a monic polynomial because so this is monic bd is equal to 1. And so d is the degree of the polynomial. Okay? So in the ring, so now consider the ring. The ring R, which is f of x modulo f of x. Okay, so as a vector space, so as an f vector space, right? This thing is d-dimensional. This is what I just said before class, but I'll just repeat this again. So this is f direct sum f x bar squared. So direct sum x bar to the d minus 1. Okay, so these are all I mean by this is that as a vector space, not as a ring, as a vector space, this set 1 x bar squared x bar to the d minus 1 is a basis, right? And then this is a d-dimensional vector space, right? This is a d-dimensional as a vector space. Okay, and on this vector space, there's a linear map. Okay, so consider the linear map. The linear map. Okay, and we're going to call it psi of x bar. So in the notation here, let's just make this clear that x bar is x modulo the ideal f of x. Okay, so it's the residue class. This is an element of the ring R. Okay, so we're going to define a linear map, psi, like this, from R to R. And it's going to be defined by psi of x bar of any element R is just going to be x times R. So this is just multiplication right? This is the multiplication by X bar map. Okay? And if I look at this multiplication by X bar map, right, then so what do we have? So if I look at this multiplication by X bar map, then let's look at what it does to the basis elements. Okay, so, and first of all, we have this basis thing here. So let's write this out. Let's write out what this looks like. In our basis. Okay, so what we're going to do is we're going to let 1 correspond to the vector 1, 0, 0, that first elementary vector. X bar, this corresponds to 0, 1, 0, 0. So maybe we'll do the first 3 entries. And then X bar squared is, 0, 0, 1, and it goes on, and it has all zeros. Okay, so, and then this continues. Okay, so then x to the d minus 1 is the one with 1 in the very, very bottom entry. Okay? Okay, and so we know that, okay, so we have that psi of 1 is x bar, psi of x bar is x bar squared. Okay, and it continues like this until we get psi of x bar d minus 1. So this is x bar to the d, and now this is equal to minus b0 minus b1 x bar minus b2 x bar squared minus dot 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 minus b d minus 1 x to the d minus 1. Okay, because this just wraps around, because in the ring R, f of x is equal to 0, right? So f of x bar is equal to 0, so you can solve for this thing. So what I did is I essentially took this thing here. You set this thing equal to 0, right? And then you can solve for x to the d minus 1, and you bring all the other stuff to the other side, right? That's what gives, so this thing here, setting that equal to 0 is what gives this one. Okay, and so then if we were going to write it out in matrix form, so this this elementary vector goes to this elementary vector. Okay, so in matrix form, with respect to this basis, we have that psi of x bar. So this is with respect to the basis. 1 x bar squared x bar to the d minus 1, and corresponding in this way, setting up this bijection that I did above, right? This thing looks like, okay, so what does the first one get sent to? It gets sent to 0, 1, 0, like 0, okay? The second one gets sent to this one, 0. And then the third one gets sent to 0, 0, 0, and then it'll have a 1 down here, but it keeps going. So maybe I should not include this one, right? Okay, then this continues, dot, 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 dot. And then in the last column, which is the x to the d minus 1 column, we have minus b0, minus b1, minus b2, dot, 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 and then minus b to the d minus 1. Okay, so what this is it looks like this identity matrix, an identity, the d by, so this is the d minus 1 by d minus 1 identity matrix. Okay, you have zeros here, right? And then you have the coefficients of the polynomials. Okay, so this thing here is called the companion matrix. So this matrix has a name. So this matrix has a name, and it's called the companion matrix. This is called the companion matrix. So let's do this. So the matrix is called the companion matrix. Of f of x, an element of f of x. So f was a field. Okay, and it has a nice property. So we use the notation C of f for the companion matrix. So it's what multiplication by the residue class looks like. That in that quotient ring. Okay, so that's what this companion matrix is. Okay, and so it has a nice property. Okay, so one of the nice properties is that the characteristic polynomial, if I do xi minus c of f, so this is f of x, right? So this is the characteristic polynomial of the matrix C of f, right? So yeah, so this is a nice theorem that you can check. So this is maybe we'll put this one as an exercise. Yeah. So yeah, so you want to just I think you can just do this by a straightforward like using the definition of expansion of like you multiply times an entry and then you take the minor, right? And then you alternate signs doing that. And I think you can prove this directly, maybe by going down the last column. Yeah. Okay. So you might need to do more. I don't remember exactly how the proof of this goes off the top of my head. Okay, so that's all I wanted to say. It kind of had to do with what we were talking about earlier in the basis. Okay, so I talked about companion matrices. Now let me tell you what a norm is. This is sometimes useful. So norms. Okay, so given alpha in f of x modulo f of x, okay, what we can do is we can, alpha looks like, I don't know, a0 plus a1 x bar plus blah, 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 plus a d minus 1 x bar to the d minus 1. Or maybe we should use c. Let's use c's because I'm using a's later for something else. Okay, c's. Oh. Okay, c's. Okay. It doesn't really matter what this is, but one can also define psi of alpha. Okay, this is R, from R to R. So this is a d-dimensional vector space. This is d-dimensional. Okay, and what can you do? So if we do psi of alpha, okay, applied to some element R is just alpha times R. So this is an F linear map. Okay, and so we define the norm of alpha. So this is not the Euclidean norm, and this has nothing to do with the Euclidean norm. This is, we define the field norm. Let's call this the ring norm of alpha to be here. N alpha is equal to the determinant of psi of alpha. And so this is basis independent. Okay, so let me say some facts. One, this is basis independent. Two, n alpha beta is n alpha times n beta. And the third thing is that for integer rings, so if, okay, so this is kind of a harder thing to prove. So if alpha is an algebraic integer, so that means that, so this means that, like, say, f of x is irreducible. And alpha satisfies a monic polynomial with integer coefficients. Okay, and so an example of this, so this is an example of this is alpha is an element of z adjoint, or alpha is an element of z adjoint beta. Oh, let's see, is that quite right? Where beta, the minimal polynomial, the monic minimal polynomial of beta has integer coefficients. Okay, so I had to say a bunch of words here. So if alpha is an algebraic integer, I gave you lots of examples, and I gave you the exact definition, right? Then n alpha is an integer. Okay. So all right. So the only reason I said this is because sometimes, so I haven't even given you the first proof of the showing something's a UFD, but I posted a link in the chat where so sometimes, okay, so let me just say the use case of norms. Okay, sometimes you can use field norms to show, okay, one, sometimes you can use field norms to show an element is irreducible. To show, let's say, to show a ring is not a UFD. E.g., z adjoins square root of -5. And there's an example of this in the text, or in the chat. The second thing that you can do is sometimes, not often, but field norms are Euclidean norms on the ring of integers. So another way to define the field norm is if you have an irreducible polynomial, it's the product of the Galois conjugates. Maybe you've seen that one before from previous semester, right? Okay, so e.g., so for this one, e.g., z adjoins square root of -1, right? So this is a ring of integers, and the field norm here actually turns out to be the Euclidean norm in order to prove that it's a Euclidean domain. Okay, so this construction where you take determinants works. The way that I defined it, I think a lot of them will be singular, but if you don't impose irreducibility, but most of the time this thing will be, the case we want to look at a lot of the time is when that's irreducible. Okay, all right. So that's all I wanted to say about companion matrices and field norms. Okay, so this is kind of like an aside here. Okay, now I'm going to show you how to show something's not a UFD. Are there any questions on this? On these two little things, these two little doodads? So the companion. So let me just say, the companion matrix is something that I was going to talk about anyway when I was going to do modular PIDs. But since we were already talking about tricks with bases of these rings, you know, as a vector space and what the multiplication looks like, it was natural to just do this now. Okay. Any questions? Okay. I'm going to show you an example of how to prove something is not a UFD. Okay. Okay. So